Let me start with a few introductory remarks. The VOT initiative was established in February 2013 as a response to the fact that the consensus on performance evaluation of visual trackers was missing, which made objective comparisons of tracking results across different papers almost impossible. The main goal of the VOT initiative has been to establish performance evaluation standards and consequently contribute to the development of better visual trackers. The VOT has been built on 4 pillars: on carefully designed datasets, on new and unified evaluation measures and toolkits, as well as on creation of a platform for discussing evaluation-related issues through organization of tracking challenges. This has led to the organization of yearly challenges, starting with ICCD 2013. The present challenge is the 8th in the series. Initially, the VOT considered single camera, single target, model-free causal trackers applied to short-term tracking. Over the years, the VOT has been expanding the number of challenges based in part on the feedback from the tracking community. New challenges have also led to new and improved evaluation protocols. This year we have 5 challenges: short-term tracking challenge, short-term real-time tracking challenge, long-term tracking challenge, RGB plus thermal short-term tracking challenge, and RGB plus depth long-term tracking challenge. For those of you who are less familiar with the VOT challenge participation, let me briefly mention the process. The participants download the toolkit and the datasets, and the toolkit then automatically performs the evaluation experiments. The participants then submit the raw results, which are evaluated, as well as the tracker code, which is needed for the verification process. Based on the results, a co-authorship of the paper reporting on the VOT challenge results is offered to the participants. Besides the results of the challenges and the winning trackers, this workshop also features a number of contributed papers. They were solicited in 2 rounds. In the first round, as papers prepared and submitted especially for the workshop, and in the second round, as high-quality papers that have been rejected from the main conference. The VOT 2020 Program Committee has reviewed the papers and selected 6 for the presentation of the workshop. Let's have a look at the workshop program. In a minute or so, we will start with the reports of the results. Matej will present the short-term, real-time, and long-term tracking challenges. After a short break, Michael will report on the RGB plus thermal tracking challenge, and Yoni will present the results of the RGB plus depth challenge. The results session will be followed by the poster spotlights. You can have a look at the longer versions of the papers during the offline session. The next online session will start at 6 p.m. UTC+1 with presentations given by the winners of the different tracking challenges, and will conclude with a panel and closing remarks. Just a few remarks regarding the interactions with the speakers. Please write your questions to a box. The moderator will then convey the questions to the speaker. Please note that the sessions will be recorded and later uploaded to the ECCD webpage. Let me conclude my introductory remarks with a big thank you to all the people that have contributed to the workshop. This includes the authors of the submitted trackers, the authors of the papers, and last but not least, the VOT committee who have organized the challenge and performed the evaluation of the submitted trackers. Many thanks also to the VOT 2020 sponsor, University of Ljubljana. Now I would like to invite Matej to start his presentation. Thank you.
Thanks, Aleš. Let me just share my screen. Screen 2. All right. Okay, thank you, Aleš. Good morning and good afternoon and good evening to all the audience. In the next 30 minutes or so, I'll present the 3 of the 5 visual object tracking challenges. And these are the VOT short-term, real-time, and long-term tracking challenge. So I'll start by outlining these 3 challenges, and I'll focus on the novelties that we introduced to these challenges this year. Then I'll go into results overview, and then at the end, we will announce the winners. So first, the short-term and real-time challenges. Now, the short-term challenge was actually the first challenge introduced in VOT back in 2013. And the aim of this challenge was to promote development of trackers that can track for as long as possible, but assuming that the target is always visible and within the field of view. So this challenge considered single target causal trackers that are required to report location at each frame as the new frame arrives. And whenever a target, whenever a tracker would drift off the target, like for example in this case here, we consider that a failure and the tracker is reset back to the target at a later frame. So this is what we called the reset-based formulation of the protocol, and it has been basis for all of the VOT short-term tracking challenges and the measures that we've developed over this protocol. In particular, we've developed 2 basic measures, which are the accuracy and robustness to measure the different aspects of the tracking. And later on, we also proposed a measure that in principal way combines these 2 basic measures into a single score by which we rank trackers. Now, in reset-based protocols, you have to keep in mind that initialization point will affect the tracking performance. So for example, let's say that you initialize your tracker at this frame here, the tracker tracks and then fails at some later point. This is detected by the toolkit, and the toolkit will reinitialize your tracker at a frame after that, or a few frames after the failure. And then your tracker tracks again comfortably for a long period, and then it fails again at some later point. Now, but if by some coincidence, the same tracker reported a slightly different bounding box at this frame, such that the failure would not have been detected on this frame, but let's say at the frame just after that, then the initialization point would also be moved to a later frame. So now you have changed the initialization frame, and if this initialization frame is more favorable to tracking than, for example, this one here, let's say that the target is better positioned and better visible here, then it might happen that the tracker will continue to track, and this time without failure. Now, if the trackers are not very robust, and this was the case in 2013 and a few years later on, if that's the case, you will not really observe this, or in the measures you won't really see it, because there'll be other things why your tracker is failing. But it will introduce a substantial noise when comparing really, really robust trackers. And recently, the tracking field has developed, and the trackers have become much more robust. So this is no longer a negligible effect. Another important component in the reset-based protocols is how you define a failure. So back in 2013, if a tracker drifted off the target, then that would be considered a failure. I mean, definitely the tracker failed at that point, and it would not have recovered back to the target, at least not by tracking design, maybe by pure luck. So, detecting a failure by zero overlap, was sort of the right way to go. But again, now trackers have become much more robust. And in modern trackers, we see that they're so robust that they might just momentarily jump off the target for let's say 1 frame, and then immediately jump back to the target in the next frame or a few frames later, if not reset. So what we are seeing here is now trackers being able to recover from what we call a short-term failure, let's say a local glitch. And to keep pace with the modern trackers, and to promote this ever more robust trackers that might even resolve short-term failures, we have, well, revisited our evaluation protocol and the performance measures. So in VOT2020, we are introducing a new short tracking performance evaluation protocol, which we call the VOT anchor-based protocol. Now, the general idea in this protocol is that we place predefined anchor points throughout the sequence, and the tracker is initialized from each of these anchors. So the tracker is initialized, and then it tracks in the direction that would generate the longest possible sequence of frames. So for example, if you initialize the tracker here, it will try to track until the end of the sequence. However, if you initialize the tracker, let's say here, it will track back into the sequence towards the start. Now each anchor does generate a subsequence, and these are the subsequences from which we compute the performance measures. So by moving from tracker-dependent initialization points to the anchor points, we have now removed the potential noise that would come from different trackers failing on different points, thus changing these initialization points. Another thing that we revisited is the definition of failure, such that we account for short-term failure recovery. And well, the protocol is very simple. So if the predicted bounding box from the tracker, if the overlap between the predicted bounding box from the tracker and the ground truth bounding box, if that overlap falls below a low threshold, but your tracker is able to recover back, increasing the overlap within a span of few frames, then this is considered a short-term failure and actually a recovery, and we don't penalize this. However, if your tracker does not recover from that, then within a predefined time span, then we would consider that a failure, and we say, okay, the tracker failed at this point. Okay, so with this definitions of the protocol and the failure redefinition, we have redefined the core 2 measures in VOT, which are the accuracy and robustness. So the accuracy measures, how accurate your tracker is when it is on the target, and robustness tells you something about, regardless of the accuracy, how long can a tracker fail, or a tracker track, or whether it fails some way along the see whether just to check, I think we're run out of electricity here. Can anybody confirm that you can hear me?
We can hear you.
Okay, thank you. Something weird happened here. Okay, thanks. Sorry for this glitch. Okay, so with this, we've redefined the accuracy, and the accuracy is the average overlap of the successfully tracked period. And robustness is the percentage of the subsequence which is successfully tracked. And apart from the accuracy and robustness, we have redefined the core or the primary performance measure in VOT, which is the expected average overlap. And this measure combines in a principled way the core two measures, the accuracy and robustness. Okay, another thing is that we've noticed, and I'm sure you all have, that computer vision has substantially evolved over the past few years, and so did the tracking subfield. So we feel it's time to raise the bar on the tracking output requirement. So from this year onward, the short-term trackers on the VOT short-term challenge are required to report target localization in form of a per pixel segmentation mask. So this is a strong contrast to the previous VOTs, where we would consider target location as a potentially rotated bounding box. But we feel, the field has advanced so much that segmentation masks are now possible, and actually a bounding box is a sort of an approximation of a target segmentation, but it's a very poor approximation. And from our experience, it's also very difficult to place a very accurate ground truth bounding box. We've made tests where different experts were placing the bounding boxes, and we always ended up with several bounding boxes, and all of them should have been considered as ground truth. So by moving to the segmentation mask, we are now reducing that uncertainty, as well as pushing forward sort of the, we hope, the development of trackers. And the trackers are evaluated against a ground truth segmentation mask as well. So this year, the VOT short-term trackers are evaluated on the VOT short-term 2020 dataset. As in previous years, this dataset is composed of the public dataset, which contains 60 sequences, and we also have a sequestered, the hidden dataset, with equal number of sequences. And the sequestered dataset is the one which is used to identify the winners. Now, both of these datasets are refreshed versions of the last year's datasets. We've removed and replaced some of the sequences. And most importantly, all of the frames in all of the sequences have been manually segmented. So here on the right-hand side, you can see comparison of the ground truth bounding box from previous VOT challenges. You see this rotated red thing. And in blue, you see sort of the output expected from the trackers submitted this year. And again, all of these sequences are annotated per frame with various attributes. This is the same as in previous VOT challenges. Okay, so about 4 years ago, we noticed that many trackers that were top performing were really complicated in design, which made them slow and not really appropriate for many applications. So in response to that, we've introduced a real-time challenge, and that was in 2017. And the goal was to promote development of better tracking designs, and to say that speed is also a very important component in visual object tracking. Now, the evaluation protocol and the measures are the same as in the VOT short-term challenge. The only difference is that the trackers are required to output frames at higher than real-time frame rate. So you have to report the frame, or sorry, you have to report the target location before the new frame arrives. And a winner is identified on the public data set, not as in the short-term challenge where we use the sequestered data set. So this is self-evaluation, and we announce the winner based on the public results. Okay, so the last of the three challenges that I'm presenting today is the long-term tracking challenge. Now, this challenge started back in 2018, and it was designed to promote development of trackers that would be capable of tracking over a huge number of frames in realistic surveillance scenarios, right? So these trackers sort of are supposed to determine when the target has disappeared from the field of view, and once the target re-enters the field of view, they're supposed to detect that the target has reappeared, and they have to detect, relocalize the target. So there are many challenges in this. For example, how to robustly update your visual model. You know, given that the target is going to be occluded and disappear many times, there's going to be distractors. How do you build a robust detector from, you know, only few, you know, certain observations, and how to design an efficient detector that will be able to redetect the target while the target is changing its appearance. Right? So many challenges to be addressed here. This year, the VOT long-term trackers were evaluated on the VOT long-term tracking 2019 data set. So this is the last year's data set. This is a specially designed data set for long-term tracking. It has pretty long sequences, and each sequence contains many target disappearances. And the targets disappear for quite a long period, so a number of frames. In this challenge, the trackers are initialized in the first frame, and they are left to track until the end of the sequence. So we don't try to detect failure or reset the tracker. And the tracking properties that we want to measure are localization, accuracy, and detection of target presence and target loss. So in 2018, maybe even, we've designed specific measures that measure these tracking properties, and these are the tracking precision, tracking recall, and the tracking F measure. And the winner is identified along the tracking F score. Okay, so with all of these protocol modifications that I mentioned, and due to the fact that the whole tracking field, while it was primarily, you know, sort of writing trackers in MATLAB, you know, now most of the trackers are written natively in Python. So we decided to also rewrite the toolkit in Python, and now the new toolkit implements all of the new experiments and the performance measures. And of course, it does not support only Python trackers, but actually trackers written also in other languages, because it uses the VOT tracks protocol. So that's a protocol proposed for communicating between the toolkit and the tracker, regardless of the language in which the tracker is written. So this is the new toolkit. The previous MATLAB versions of the toolkit are now obsolete and will no longer be maintained. Okay, so now we come to the VOT short-term and real-time challenge results. This year, we've evaluated 37 trackers in these two challenges. The tracker designs more or less follow the trend that we have observed in the previous VOT challenges. But what is different now is that you know, we've changed the requirement for the output of the target location, so to segmentation mask. And it's actually great to see a very strong response in the community. More than half of the trackers that we tested actually report target location in form of a segmentation mask. So it's really nice to see the community is able to respond so strongly and so fast. And it really led to some interesting results that you will soon see. So here's the results for the VOT short-term tracking challenge. So the results on the public data set, I'm just showing this now. So here you see all the trackers ranked with respect to the expected average overlap on the public data set. And if we look at the top 10 performers on this data set, it turns out there are some commonalities shared between these submissions. First, all of these trackers use a pre-trained ResNet 50 backbone as their core backbone. And all of the trackers are correlation based. So either they use deep discriminative correlation filters, or they use Siamese correlation filters. And for the localization, all of these trackers provide a segmentation mask. It's also interesting to see that still many of the trackers apply region proposals to address the changes in, to address the aspect changes in target location, and to, in a way, constrain or help the process of further segmenting the target from the background. Now, a detailed analysis shows that the top trackers are also among the most robust trackers. And when we look at the difficulty levels of the different visual attributes, it turns out that the occlusion is the most challenging attribute. So occlusions cause most of the failures and mostly reduce the tracking accuracy. Now, to evaluate how much the tracking field has advanced over the last few years, we have looked at the trackers that used to be considered as strong baselines or even state-of-the-art last year. And we see that these trackers are now at the tail of this ranking, which indicates quite strong submissions to the VOT 2020. Moreover, if we look at the VOT published state-of-the-art bound, so this is a bound that we compute by looking at trackers that were published at major computer vision conferences and journals in the last 2 years, and we average their performance. And that constitutes the state-of-the-art bound. So any tracker exceeding this bound is considered the state-of-the-art tracker according to the VOT 2020 challenge. And we see that nearly 50% of submissions exceed this state-of-the-art bound. So these are really strong submissions. Now, by introducing the segmentation output requirement in our challenge, we have implicitly narrowed the gap between the short-term tracking and the field of visual object segmentation. So to test this gap, the VOT committee took a state-of-the-art tracker from video object segmentation domain. This is a tracker published last year. They modified this tracker and they rerun it on the VOT challenge. And astonishingly, this tracker performs very well. So it's positioned up here, almost at the middle of the ranking list. So this tracker, although designed primarily for detailed video object segmentation, and that means segmenting large objects in videos, it was outperforming nearly half of the VOT submissions. And a detailed analysis shows that this was primarily due to the accuracy of the segmentation. So this tracker is very accurate, of course, by definition from video object segmentation domain. They optimize for this most accurate segmentation possible. But what it lacks is the robustness, right? So many trackers in VOT are more robust. They would fail less, track longer. And of course, this is to be expected because robustness is one of the core things that has been promoted over the years in VOT, actually from the start of the VOT. But it shows that, you know, there are things to be learned from the video object segmentation community, and surely vice versa, right? So I also believe that video object segmentation community is going to benefit a lot from closing this gap by taking things that work really well in the short-term video object tracking challenge. Okay, so just to superficially illustrate the advancements made over the last few years, I'm going to show here results for three important trackers. Now, these two trackers here, I would consider these milestone trackers because when they were introduced, they significantly affected the tracking domain. So a lot of trackers are actually based on the core algorithms introduced in these two. So this is the tracker from 2016, and this is the tracker from 2019. And this is the top performer from this year. And now I'm going to show tracking of this BOLT guy over here. So very challenging sequence because there's many similar targets here. Actually, this guy looks exactly the same as BOLT, and the scene is dynamic. So what we see is that, of course, in this superficial illustration, that robustness has improved substantially over the years, and we have observed a significant leap this year. So now we have, you know, trackers that are quite robust in distinguishing, you know, distractors from the target, and the localization is also very good. You know, the segmentation mask quite nicely delineates the outline of this target. Now, so of course the tracking has, you know, measurably and also qualitatively improved, but you know, it's not solved. You know, still there are many challenges, and just to, you know, emphasize this point, I'm showing you results on one of the most challenging sequences in VOT, so tracking white rabbit running over an avalanche. So, you know, the tracking is more robust, but not enough, right? So there's more work to do in design of better learning algorithms, distinguishing, you know, distractors from the targets, you know, using more involved visual models that are able to cope with such kind of appearance changes and so on. So lots of work still to be done. Okay, so as I said, the VOT committee evaluated and identified the winner on the sequestered dataset. So the committee took 5 of the top performers from the public dataset and rerun them on the hidden dataset. So this graph here shows for each tracker the performance on the public dataset as well as on the sequestered dataset. And what's really nice to see is that the performance is quite stable across the two datasets. You know, so this means that these trackers have not been overfitted to a particular dataset, but rather they're stable. They're you know, the results on public dataset can be generalized to other datasets. And what's even nicer to see is that the top performer on the public dataset, where, you know, when it really stands out from the other trackers, is also a top performer on the sequestered dataset, with quite a healthy improvement compared to the second best tracker on the sequestered dataset. So it shows that these are really top trackers, and this one, you know, clearly stands out. Now, I'll briefly discuss the results of the real-time challenge. So here we see ranking of all the trackers with the real-time constraint on the real-time challenge protocol. So this is what you see here. This tracker, we've added this tracker because this is the VOT real-time 19 winner. So this is the last year's winner of the real-time challenge. And we see that a lot of submissions have substantially improved their performance on the real-time domain. So we have now a strong push in performance also when we think only about the real-time constraint. Now looking at the design of these trackers, I'm showing this just sort of the, well, again, very superficial design properties of the 10 top trackers. We see that the dominant methodologies are correlation-based. So either Siamese correlation or the deep discriminative correlation filters. And actually the top two performers, they mix the two methodologies, it seems. Now, it's always interesting to look at the difference between the performance on real-time challenge and on the short-term tracking challenge. And this is shown here. So up here, we see trackers ranked with respect to the short-term experiment. And here are the same trackers re-ranked according to the real-time challenge. Now, what we usually saw in previous years was these trackers up here mapping down to the tail under real-time constraint. But this year, it's quite astonishing to see that 8 out of top 10 trackers in real-time challenge are among the top 10 trackers on the short-term challenge, right? So now this is really good because this shows that we're observing emergence of deep tracking architectures that no longer sacrifice speed for performance, right? So it seems that, you know, the challenge, the real-time challenge is working. It's sort of pushing the field towards designing efficient algorithms that are also highly accurate and robust. Okay, so finally, let's overview the results of the long-term challenge. Now, in the long-term tracking challenge, we have tested 8 trackers. And this year, all of the submissions were pure CNN trackers. So no longer are we observing handcrafted and handcrafted features and partially handcrafted algorithms. So now we see CNN architectures combined together into a long-term tracking architecture. So here's the results. The 3 top performers actually stand out quite well from the rest, and they're, you know, they're condensed also here in this part of the graph. So like in other challenges, just to measure the pace of the advancements, the VOT committee took last year's winner and rerun it on this challenge. And actually the top performer among all of the submissions is the winner from last year. Now, this winning tracker, LTDS from last year, it has quite a complicated architecture, but this architecture delivers really good performance. So just to briefly overview it, for the short-term component, the tracker uses the deep discriminative correlation filter and Siamese correlation with segmentation for frame-to-frame target localization. So that would be the short-term component. For target absence detection, a variation of the MDNet tracker is used. MDNet is the winner of the VOT2015 short-term tracking challenge. And for the redetection, a region proposal network that was introduced by MBMD tracker is used. MBMD, this is the winner of the first VOT long-term tracking challenge. But if we look at the submissions not entered by the committee, the top performer is the tracker called LTMUB. And what's interesting is that the performance drop of this tracker compared to this top performer, the performance drop is really negligible, right? So it performs nearly the same, but it's interesting to observe that LT-MUB can actually be thought of as a simplified version of this of the last year's winner. So we're also observing advancements in long-term tracking in that now we're seeing streamlined, faster architectures reaching nearly the same performance as these more complicated versions. And again, as a trivial illustration, I'm just showing here the difference in performance of this year's top performer not entered by the VOT committee and a tracker that used to be considered state-of-the-art tracker in 2017. So this is state-of-the-art long-term tracker in 2017, and this is what's been submitted this year. And you see that, you know, improvement is really substantial. You know, much better detection, much better handling of the aspect changes, and much better dealing with the appearance changes of the targets over, of course, this long period of frames. All right. So to summarize, I've overviewed 3 of the 5 VOT tracking challenges, the short-term, real-time, and long-term. In short-term challenge, we see continuation of the core methodologies. So deep DCFs and Siamese correlation are the dominant methodology in the, I would say actually in all the submissions, not only the top performers. All of the top performers provide high quality segmentation mask. So this is really nice to see. You know, the community has reacted really, really fast, and the tracking has improved in terms of robustness as well as accuracy. So that's really nice to see. So we see a substantial improvement over the last 2 years in visual object tracking when it comes to short-term trackers. But we also see improvements in terms of real-time performance, right? So the real-time challenge shows that we are witnessing emergence of deep tracking architectures that now are fast and robust. Okay. And for the long-term tracking challenge, it seems that the architectures have stabilized over the last 2-3 years. So now we have, you know, more streamlined, faster long-term trackers than we had last year, and without performance drop. But of course, more work is required on this domain, especially in terms of efficient target appearance learning over longer time spans and efficient detector learning, so that it doesn't confuse similar targets for the actual target. Okay, so now we will announce the VOT winners for these 3 challenges. Now, the winners of the VOT short-term tracking challenge are the authors of the tracker RPT. These are Haitao Zhang, Linyuan Wang, Xiang Ma, Wei Lu, Jun Yin, and Miao Cheng. The winners of the VOT real-time tracking challenge are the authors of the Alpha Ref tracker, and these are Bin Yan, Dong Wang, Huchuan Lu, and Xiaoyong Yang. And finally, the winners of the long-term tracking challenge this year are the authors of the LT-MUB tracker, and these are Kenan Dai, Dong Wang, Jianhua Li, Hutuan Lu, and Xiaoyong Yang. Now, on behalf of the VOT committee, I'd like to congratulate all the winners for their fine achievement and their excellent trackers. The winners are going to receive this VOT winner plaques for the different challenges. You'll receive them over snail mail. And in addition, you will receive this beautiful VOT 2020 t-shirts, which have been incidentally printed only for the VOT winners and the committee. So, so they are in limited edition. So, you know, don't let me catch you try to sell this on eBay. You know, they're worth a lot, collector's item, so to speak. Okay, for the audience, I'd like to point out that you will be able to hear the talks from the winners in the second live session, which will take place at 6 o'clock UTC +1 time zone. And you'll be able to hear what makes this tracker work so well, and you'll be even able to ask questions to the winners and discuss things. Okay, so this concludes this presentation. I'd like to just quickly thank the VOT committee for helping organizing these 3 challenges. I'd like to thank everyone who have participated in these challenges, and also on our sponsor, the University of Ljubljana Faculty of Computer and Information Science, for sponsoring the plaques and the t-shirts. Okay, and last but not the least, of course, thank you all for joining this presentation, and I'm now open for questions. Thank you.
Thank you very much. There is one question in the chat box. It's about how to calculate the score for short term tracking when it is lost just for a few frames. You actually see the question, and I would
let me look at the question. What if the tracking continuously? Aha, okay, yeah. No, let me just. I noticed that when calculating the robustness score, lost frames are also involved. So are we talking about the accuracy? When calculating robustness score. So no, I mean, like, if we're talking about robustness score. Okay, no, I see. Okay, so it's like this. So I think the question is, sort of, we are computing robustness as a percentage of successfully tracked frames, and why don't we remove? Why don't we label the frames of short-term failure as unsuccessfully tracked frames, right? So this is essentially, I think this is the question. Well, we want to establish how long, so what is the length of the tracking length? We want to establish what is the length of the successful tracking up until the tracking has become unsuccessful. So this is the definition of our robustness score, and that's why short-term failures are no longer part of the failure definition, and that's why we don't label those as failure, because they are short-term failure and the tracker has been able to recover from that. So I hope this answers the question.
Thank you, Matej. There seem to be no further questions. So if that's the case, then I would suggest we make a short break and then we continue in 5 minutes or so. I hope you enjoyed the first presentation, Matej. The next presentation will be given by Michael, who will report on the results of the VOT RGB plus thermal tracking challenge. Michael, please.
Yeah, thank you very much, Alesh. Good morning, everybody. I hope the sound is good. Please let me know if it's not. So I will now present the results of the RGBT challenge, sub-challenge within VOT 2020. Now you might wonder, what is the purpose of having the extra thermal channel and video? And indeed, there are many applications, and this is because RGB and thermal imagery are complementary to some extent. You can see this in the video that plays on the slide. So to the right, you can see the thermal imagery, and to the left, RGB. This is a recording at night, but still, like, the traffic light is only visible in RGB, whereas the cyclist is hardly visible in RGB, but it is in the thermal imagery, in contrast to the traffic light. So this information is really complementary. Now, for those of you who are not familiar with thermal imagery, I would like to say a few words about the physics behind. So in this diagram, you can see the visible spectrum to the lower left from red to violet. And if we then go to the longer wavelengths, we come to the infrared part. And it starts with near infrared, etc. And then we have an area where the atmosphere blocks infrared light, and then there is what is marked here as LWIR, and that is usually what is understood as thermal imagery. Definitions go a bit apart here, but this is what is used in the VOT challenge. So now I said there are many applications of thermal infrared, and you can use it obviously in scientific applications, not only to evaluate, but also to measure effects in scientific experiments. It's often used in security applications, fire monitoring. So you could think about like a garbage hill that starts to heat up and starts to burn, and you want to automatically clear the fire. Search and rescue, if you look for people from helicopter. Automotive safety, the initial video I showed. Personal use, you could also use it. You could measure fever, for instance. So in the current times, this is very useful for monitoring fever of larger groups of people. And now, when it comes to tracking, several challenges occur. In particular, if you combine RGB and thermal infrared, you have two different cameras, you have two different camera geometries, you have two different camera timings, and you need to register the views, and you need to calibrate and synchronize them. Furthermore, scientific challenge is also to understand the similarities and complementaries in the two channels. And finally, relevant problems also how to fuse the information from the various channels and take advantage of this. You might argue that thermal infrared is just like a grayscale image at low resolution, but this is actually not the case. I mean, there are certain similarities, but there are interesting differences. So you could use the higher bit range, but what is, I think, most important here is on RGB images, you cannot rely on the absolute value of the RGB values, whereas on thermal infrared, you have a good approximation that the intensity corresponds to temperature. On the other hand, thermal infrared includes much less structure, edges, texture. It's easier because we don't have shadows, but we have other types of noise, in particular blooming, low resolution, dead pixels are problems. Some years ago, we therefore collected a data set from external sources and internal sources, annotated and unannotated the annotation ourselves. And this data set, the Linköping thermal infrared data set, was the basis for the first infrared challenge in VOT. And one of the outcomes was, among other things, that it's really relevant to have a separate challenge on thermal infrared because the results deviate from the RGB. So you can see here in this diagram, particularly to the right, you see the two ellipses, and we have the relative ranking in VOT on the x-axis and the relative thermal infrared ranking on the y-axis. And the smaller ellipse to the lower right, these are methods that have a better rank on RGB, significantly better on RGB than on thermal, whereas the upper left ellipse are methods that have a significantly better rank on thermal infrared than on RGB. And this gives a clear indication that methods with different properties are more suited for thermal or RGB areas. Now, of course, if we now combine the two channels, we would like to combine a tracker that is particularly strong on RGB with one that is particularly strong on thermal infrared. In the data set, thermal infrared data set, we did similar annotations to those in RGB short-term challenge, but some things had to be changed. So for instance, dynamics change and temperature change had to be introduced, whereas like shadows, for instance, are not relevant. Similarly, for the per frame attributes, also here dynamics change had to be introduced rather than illumination change. This was also the basis for the annotation of the RGBT dataset. So for the last year's challenge, we chose the RGBT234 dataset from the paper of Li Liang, Lu, Zhao, and Tang from 2019. The dataset that consists of 234 sequences, and from this dataset, we selected 60 sequences for the public dataset and 60 for the sequestered dataset. The attribute of illumination change turned out last year to be, or the dynamics change not to be that relevant, so we skipped it for this year actually. And one of the main challenges was to prepare the annotations in a way compatible with VOT. So for last year's challenge, what we did was we changed from the original axis aligned annotations to rotated bounding boxes. And for this year, we attempted to use segmentation masks as well. I will get back to that a bit later. There were several issues with the re-annotation. One is the spatial accuracy. So the original annotations were partly problematic, and by re-annotating, this was significantly improved. Another problem was synchronization. So you can see in the lower part of the figure to the right, you can see the thermal and the RGB channel, and the green box marks the pedestrian in the RGB, whereas the red in the thermal. So these are from the same timestamp, and you can clearly see that there is a problem with the synchronization. So this can always happen, that you have a local desynchronization, and this causes problems, of course, for the tracker, but also for the evaluation. Now, for doing the annotation, the re-annotation, what we did was that we first created segmentation masks individually for the two channels. Like in the upper figure, you can see the white contour and the thermal channel, and then we fitted automatically rotated bounding boxes. So this procedure is based on these two papers mentioned here. So we use semi-automatic annotation procedure that is based on a previous paper on video object segmentation from CVPR 2019 from my lab, and on a method for the automatic determination of the bounding boxes that is from Jirimata's group. So what we what we did in order to improve the results from the video object segmentation is the following. So we have some manually annotated keyframes, or anchors, you could call them also. And we track forward and backward in both channels. And whenever we notice that the intersection of a union goes below a certain threshold, we start to hypothesize a failure. And if this is then confirmed, we add another manually annotated anchor or keyframe, like here J11 or G21. And then we repeat from that point in both directions again. So we always have in all segments 2 different directions in 2 different modalities, and we can always check for the consistency. The whole procedure is summarized in this figure. So we have some manual annotation, we apply the automatic segmentation, we detect the failures. If we detect a failure, we increase the manual annotation, and we loop this until we don't have any failures anymore. We fuse the modalities, and this generates the tentative annotations, which are finally manually refined. The results of this procedure, well, first of all, we got the annotation used last year, and we could save about 78% of the workload compared to full manual annotation. But there is actually a synchronization issue even here in the annotation. We use thermal infrared as a reference, but the result, or mostly due to the synchronization, was the spatial accuracy was not perfect. Actually, the expected average overlap is just 75%. Still, this is what we had and we used for this year's challenge, but the synchronization issue was so severe that the expected average overlap of the segmentations were too bad to be used in the assessment. So we stayed with the assessment by bounding boxes. Otherwise, we used the same procedure as for the short-term challenge. And similar to the short-term challenge, we use the top ranked trackers on the public data set to select the set for the experiments on the sequestered data set, and the top ranked tracker on the sequestered data set is the winner of the challenge. Now let's look into the submitted trackers. So 7 trackers were submitted in total, which was a bit beyond expectations, and 2 by the committee. Sorry, 5 were submitted and we had 7 total, so 2 by the committee. These were the best 2 performing from last year, MFDIMP and Siam WT. Of the 5 submissions, we had 2 respectively 3 in the ST 1 and 0 class, but all 5 used a uniform dynamic model and a discriminative model or holistic representation. More interesting are the differences. So 4 of the 5 were single stage based on DCFs, and 1 was a multi-stage based on Siamese networks. That was DFAT. And 1 makes use of subspace method and handcrafted features actually. That was the M2C2 FRGBT. The other 4 make use of deep features, and 2 even trying the backbone on the fly, AMF and DFAT. And 1 is using RANSAC. Now the results on the public data sets, all top 5 trackers use CNN features, so they handcrafted drop out quickly, and 3 use DCFs, 2 Siamese networks. And the second and third ranked 1 use backbone training. You can clearly see that the performance is very close. So in the AR plot, but even the EAO curves are very close to each other. Maybe M2C2 FRGBT is dropping a bit below, presumably due to the manual features. Just to give you an impression about the performance, I have a short video of AMF on one of the sequence, which is shown here. And in the beginning, the sequence is pretty easy, but it becomes quite difficult when the person walks closer to the car. and there's also partial occlusion, and this is one of the sequences where all the others failed actually. So one of the more difficult ones. Okay, so some further results. Again, the overall EAO score is strongly correlated to robustness than to accuracy, and robustness is most challenging for occlusion. So this is the same outcome as for the ST challenge. And in contrast to the ST challenge, we have a quite changed order of the ranking on the sequestered data set. So you can see here on the sequestered data set, we have the previous year's methods, SIAM-WT and MFDM, provided by the committee that performed first and second. And the third performing method, so the best performing submission, is DFAT on the third rank here. And this, we come to the winner announcement. So the winners of the LGBT challenge are Li, Tang, Xu, Xu, Wu, and Kittler, with a method Decision Fusion Adaptive Tracker, DFAT. And you will see their presentation in the next live session. So to round up, CNN features are dominating also in the RGPT challenge. In contrast to the ST challenge, the ranking has changed significantly on the sequestered data set, which indicates a certain amount of overfitting on the public data set. The overall performance decreases only slightly on the sequestered data set. Last year we had a quite severe decrease, but this has been much lower this year. And in combination with a much more similar performance of all the submitted methods, it seems that performance also seems to converge here on the combined challenge. Robustness is still most important, and occlusion is the largest challenge. For the future, we would really like to attract more participants, and we would definitely try to address this problem of the misalignment or synchronization errors so that we can switch to segmentation-based evaluation. So let me just thank all the contributors to the RGPT challenge and our sponsor, and please ask your questions in the chat. Thank you.
Thank you very much, Michael. There is one question, and this is regarding the synchronization. What is the reason that IR cameras cannot maintain a fixed frame rate? Is this somehow related to the synchronization issues?
So thermal cameras, they are a bit special in the sense that they are radiometric, and several models need to be recalibrated in between. So there's a short break in the image acquisition to do the recalibration, and usually during the period of the recalibration, no frames are sent. So this can lead to a slight change in the frame rate, or it could lead to frame drop, or it could lead to some other effect on the sequence. It depends a bit on the model. But in general, thermal infrared cameras are less reliable when it comes to constant frame rate. And it's unfortunately not sufficient just to have a global adjustment of the relative sync. You have to do a local analysis of the synchronization between the two channels, and it's hardware dependent, but the hardware is not visible in the data set, so we can't know which hardware was used. So it's a bit tricky. It's a difficult estimation problem.
Thank you very much. I think there are no further questions. So, Michael, thank you very much again for the presentation. And the last presentation related to the VOT challenge results. So I would like to invite Yoni to present the results of the RGBD long-term tracking challenge. Yoni, the floor is yours.
Okay, I hope you can hear me. I'm just asking, are you able to see my mouse when I move it?
Yes.
Cool.
Hear you and we can see.
That will help me with my presentation because I have no timings at all. All right. So the people who were active on this RGPD channel were Ales, me, and then of course Song and Chinu, who did a lot of kind of like testing of the methods and I think debugging of the new toolbox and so on. But let's jump to the thing. The first thing, why to add depth? I think this is a very important question because if this would be, VOT would be in the robotics community, we would be asking why to add RGB. Because I mean, depth provides important information. And for the robotics community, I think it is still far more interesting than RGB because they prefer to use those TOF sensors and LiDAR sensors and so on. So why depth? First of all, it provides us 3D sensing, which means that in robotics, if you want to grasp an object or manipulate your environment, if you use only the RGB, it makes things so much more difficult. If you use only the depth channel, I mean, you are naturally in 3D, and then depth is kind of like similar to thermal camera. It has a connection to the physical world and three-dimensional world there. But as most of the people are still most familiar with RGB tracking, we can ask what kind of things are easier if we add the depth channel. If you can see this example here, there is a red rose, and then there is some kind of like object that is occluding this red rose there. If we are looking for the RGB result, RGB, so the color channels only, what happens is, for example, this bottom line is one of the state-of-the-art trackers. It kind of like combines the information of those two things and continues to track actually this object and not anymore the rows at all. While if we look the depth channel, we can see that there's a clear difference in the depth information, and then it is easy to, for example, on the third row, to segment the actual object and use this information to help to track the kind of like the correct object, or to detect occlusion when the object is out of sync. So these are kind of like things how the depth can help with RGB. Then there are a lot of challenges. For example, people are mostly vision communities interested about the RGB, and then there is a various ways to combine RGB and the depth, and the typical way is to just add the as a fourth channel to your tracker. It's a bit problematic nowadays with the deep learning because the last line here, there is much less RGBD tracking data than RGB data. So basically you need to use some other sources of the depth and RGB information if you want to really train your system from the scratch. One option could be, I don't know that any submission used this idea to switch between the RGB and D. We know that, for example, this is a rather popular approach in SLAM community, in robotics, when sometimes the scene doesn't have rich text, but the depth information provides us rich information, and vice versa. There is a lot of examples when the robot is moving in the corridor and so on, when one of these modalities is better. Then let's jump to existing datasets. I think the prior datasets before the VOT was PTP and STC datasets that were available, and those were used in those very few works studying RGBD tracking. They have a lot of kind of like, not problems, but limitations. There is only a small number of those sequences, as you can see, 36 versus 100, and those sequences are rather short. They are 5 to 15 seconds, so I mean, not suitable for long-term tracking evaluation. Depth in those datasets is quite often rather stable. So it means that there is no in-plane rotation of those objects. That makes kind of like depth even preferable modality for some of those example videos there. And then single sensor is used. I don't know how difficult that is for overfitting, but especially with the deep learning methods, that it might kind of like find some weird readings from the sensor that it can use for tracking and so on. The VOT RGPD 2020 dataset is actually the same as 2019. We plan to collect a sequestered dataset for evaluation, but then there was this little thing called COVID that kind of like destroyed those plans. So we were still using the same 80 sequences. They are much longer than in any of those previous datasets. There is a frequent and long-lasting target disappearances because we really wanted to study the read detection of those datasets and so on. There is a significant 3D pose changes. So I mean, those objects are not planarly moving in kind of like orthogonal to the depth, but they are rotating and then translating at the same time. We really wanted to challenge also the depth channel in that sense. We are using the traditional axis aligned bounding boxes, and then we assign some kind of like attributes there to study later that if there's some kind of objects or some scenes that are particularly difficult for RGPD tracking. We wanted to test several different sensors. We had a typical kind of like depth RGB sensor like Kinect. Then we made a pair of a high quality TOF sensor and high quality RGB camera. And furthermore, we made the stereo camera pair, which is popular in robotics and much more useful when you go outdoors and you have longer distances. We have indoor and outdoor sequences. We spent quite some time to align the syncing temporal dimension. That was done by using an analog clock that we kind of like use to sync those two streams, and then temporally, and then we use spatially aligned. We calibrated the system to spatially align those videos. But we are actually not now giving out the raw data, but if someone asks for the raw data, we can produce that one as well, because I'm afraid we also introduced some errors when we filled some holes in the depth channels, and when we don't provide the original measurement channels for the depth and RGB, because they are always a bit, there is a baseline, which means that some of the pixels cannot be measured with depth camera or RGB camera. The setup is long-term tracking. We have basically the methods they need to cover from occlusions, full or partial occlusions and disappearances. We are using the VOT long-term protocol for that one. As I said, there is no sequestered data, so all the results are based on the public dataset. Now we are collecting new dataset, and now we have another dataset about the same size, and we will possibly ask the authors or the submissions whether we can test those methods on our new dataset. The method should output bounding boxes and then presence confidence for the evaluation. It is a long-term experiment, no reset experiment, and then we are using the well-known long-term precision recall and tracking F-measure performance indicators for this dataset. Last year, 4 valid entries, they are there on top. The winning one was the Siam DVD. I think the same was participating the thermal camera challenge as well. This year, pretty much from the same authors, 4 valid entries. These are not, by the way, in the order of who won, but the alphabetical order. On top of that, we added some baselines, and then we took all the best trackers from all other long-term, short-term, and real-time challenges, and we tested those RGB trackers on this data as well. And these are the results. You can see that these, the 3 first ones, ATKIS, DDIMP, and then CLGSD, they were submissions of this year, and those are the 3 best performing methods. Number 4 is the best performing method from the last year. So that was the VOT RGPD winner from 2019. Then we have the 4th method for this submission. And then there is a bunch of those RGB methods. So the nice thing that you can observe from this table is that at least depth seems to add something on top of the RGB, because even the best RGB methods cannot beat these depth-based methods. one of the submissions goes behind the best RGB trackers, but all the 3 best ones are submissions of this year. Now you can already start to guess the winner pretty well, but let's study a bit more, because it is interesting that this ATGuys was performing very well and it was submitted last year. So we had a look on the last year results on ATGuys. It is the second bar here, as you can see. It is performing for most of the attributes rather well. It is the best one or the second best one, maybe third best one, but very close to the winning teams all the time. But then there is actually 2 attributes, full occlusion and out of frame occlusion, when ATGuys is performing very bad. And I think this is actually due to the reason that the submission, the valid submission from the last year didn't output the confidence values properly. So it kind of like completely missed these 2 categories. And then I can guess that only by fixing the confidence values, the ATGuys would have been the winner even last year. But later the authors will tell us how the method works. So if we look, I'm sorry about the format, it's a bit different from the last year, but if we look for the out of frame numbers, now ATGuys is this red ball there. So it is the 3rd best, and then another one, this was the out of frame, and then full occlusion. If we look that number as well, it is improved there. So I mean, the other numbers are more or less or very similar to the last year. Then we wanted to study whether there is any difficult scene types or any difficult object types for RGBD tracking. On the left-hand side, you can see the number of sequences of each type. And on the right-hand side, we actually run 8 best trackers and calculated the overall failure percentages of those. So we wanted to see kind of like, is there something which is kind of like on average difficult for all the trackers and so on. In this picture, there is no much to take home. Basically, this only shows us that there is they are the proportion between the number of different sequences and number of the failure cases is pretty much the same. So I mean, if you want to improve the tracking results, you should really focus on all the possible cases there. Some kind of summary, if you want to do a very good RGBD tracker, I would take the best available long-term RGB tracker with all the tricks and hacks available, and then I might check on which cases it fails, and then think whether I can use the depth channel to help on those cases. This seems to be the case for those submissions as well. So they use the depth channel for occlusion detection. Still open, unexplored research questions. One of them is that, can the depth provide discriminative features for tracking? If you look those videos, there is no much, I mean, the resolution of the depth doesn't provide much information about the most of the objects we have there. They almost look like plain objects in the depth channel. So this is the problem of a much weaker resolution of the this depth channel. Basically, the depth provides the segmentation of an object very well, but no details on its texture and so on, unless it is a very kind of like rough object with some kind of like a lot of gradient on its surface. So this is something to kind of like consider when we develop those trackers. Of course, most of the people know that if there would be a lot of RGBD tracking data available, they could probably train an atom tracker or something that learns to optimally use the depth information. We need to find a dataset that is suitable for that one, or collect enough of RGBD data, but it's not available at the moment. Then there is, of course, a natural extension. Why on earth do we track in 2D? Because actually most of the applications prefer to have the 3D information, for example, the robotics and autonomous cars and things like that. So we could actually, with the help of the depth channel, start to evaluate trackers in 3D. This is ongoing work at the moment, and then we have the first 3D tracking dataset now available. Winner of the VOT RGPD 2020 challenge is Guys by Triple Wang and then Lu and Yang. So my congratulations to this method, and I'm as I said, probably if the valid submission last year would have provided the confidence course, they would have won last year as well, but at least now they got their chance. So my congratulations. This is it from the RGPD challenge. Happy to answer questions.
Thank you very much, Joni. There are two questions for you. The first one is about the connection between RGBD tracking challenge and the 6 degrees of freedom pose estimation challenges. So on one hand, like 6 degrees of freedom pose estimation challenges, they usually have specific models, while RGBD is a single shot 3D tracking, or more correctly, like tracking with depth. So what would be your comments?
I would say that if you know the two problems, they are completely different. I mean, in 3D pose estimation, you typically assume that you know the object that's pose you are trying to estimate. While we are in this generic setting that there is something in the scene, we annotate it, and we should be able to track that one there. Of course, if you can make the RGPD tracking to work very well, you can automatically reconstruct models of objects, 3 models of those objects, and later you can estimate their kind of like poses there. I mean, we can probably, if we want to go to 3D tracking, then we can learn a lot from 3D 6 degree of freedom pose estimation challenges. I believe so. But you need to remember that who is the user of these methods? If we are talking about robotics, people, and manipulation, the way we measure 3D pose estimation is almost useless to those people. They don't care the accuracy of the pose, they care whether they are able to grasp that object.
The next question is about different types of sensors that are used for measuring depth. And the question is, are there any calibration problems that come with this?
We don't know. We kind of like everything is just put together. But in the future, we are thinking to throw out the stereo system. I mean, it is obvious that in indoor scenes, typically the time of flight sensor is the one to use. But if you go outdoors, then it is likely a stereo system or LiDAR that you should use there. I mean, the type of depth information they provide is very different. I might even have an example image. Here we can see the type of the stereo provided depth is very different. I mean, the accuracy is, and the resolution is even worse as compared to this top sensors. But I mean, we didn't check that. Then it should be some kind of like cross sensor experiment that we would need to perform. But now we don't have enough data for such experiment.
Thank you. There is a follow-up question. How far are we from object reconstruction for 6 degrees of freedom pose estimation given the current state of the RGBD trackers?
That's a nice question. I mean, it doesn't work at the moment. I don't believe that anyone can show a method that works for generic objects. You kind of like somehow initialize what I want to reconstruct, and then you just rotate it in front of the camera, and you would get a nice 3D model of that object. But I think it is one problem that people should solve as soon as possible, because it helps human-robot interaction quite a lot. if you can show quickly objects to a robot, and it then kind of like captures 3D model and is able to estimate pose of that object. But not solved at the moment, but I think we have all the tools to solve the problem.
Thank you very much, Joni. There are no further questions, so this concludes the presentations of the results of the VOT 2020 challenges. So I would like to thank all the speakers, Matej, Michael, and Joni, for very interesting presentations. And now Roman will take over and share the session on spotlights. Thank you very much.
Yes, thank you very much, Aleš, for sharing this morning session. I think it's for me now a minor task to introduce you to the spotlights. I would like to, before we see the spotlights, say a few words. So first of all, I would like to thank all the contributors of this year's VOT Challenge. So as Matti mentioned before, we have 7 contributions, whereas the 6 contributions will be now shown by their spotlight videos, and then later on we will have the opportunity to see longer videos of this work. The 7th contribution is about the results of this year's VOT Challenge, which will not be shown here, but which will be published as a paper, which you can then read and you can actually access later on in the proceedings and also from our webpage. I would like now to show you the spotlight videos, and afterwards I will say some concluding remarks, and then I leave you for lunch actually. So I try not to share. Oh, sorry. Just going back. Share my screen. Okay. So I will now start the video, and hopefully you can see all.
Hi, I'm Seok Choi, and this paper is about long-term tracking focused on robustness. We adopt a pre-trained short-term tracker as a baseline which combines PRDIMP and DIMP. And we add a naive random search redetection network. The main contributions are threefold: uncertainty reduction, random search with spatio-temporal constraint, and background augmentation. Firstly, the robust model should track the target consistently whenever we remove some regional background. So, we correct the tracking state according to the consistency after random erasing. Secondly, to prevent sudden detection of the similar object, we penalize the confidence score through the spatio-temporal constraint. Finally, synthesizing various backgrounds with the target image makes the model robust against the background clutter. We achieve the highest score in the recall metric, which means that our tracker is well modeled to be robust. Thank you for listening to my presentation.
So here comes the second spotlight video.
Hi everybody, Matteo Dunafri speaking. This is the spotlight presentation of our paper, An Exploration of Target Condition and Segmentation Methods for Visual Object Trackers. The visual tracking communities are currently moving forward on using segmentation masks to represent target states. In our paper, we study how to combine bounding box trackers with the most recent object condition and segmentation methods in order to obtain a target segmentation after a coarse localization. Our work can be seen as an extensive and in-depth reference to transform any bounding box tracker into a segmentation tracker. We analyzed an heterogeneous set of state-of-the-art trackers in combination of 3 conceptually different segmentation methods. Our broad study shows that the best combinations can compete with the recently proposed segmentation trackers on the VOT 2020 and Davis benchmarks. For more detailed insights, watch our 15-minute presentation or check out our paper. Thank you.
So here the third contribution now.
Hello everyone. My name is M. Phonher. In this paper, we will propose 3 mechanisms to improve the performance of Siamese network-based trackers. Firstly, we propose an anchor-free 2-stage object tracker. This design significantly reduces the model size of the original two-stage trackers. Secondly, we revisit the design principles and training procedure of Siamese FC. A simple and strong baseline is produced. Last but not least, we propose a position-sensitive convolutional layer that can be stacked after backbone of Siamese FC trackers to achieve an even higher tracking accuracy for both single-stage and two-stage trackers. This module can keep the size of receptive field to be stable while extracting more semantic features. Ablation study and state-of-the-art comparison shows the effectiveness and advancement of the three parts. Thanks. For more details, please refer to our paper.
Sorry, there is no sound provided by this video, but I can inform you that this basically is the actually the winner of the short-term tracking challenge, which is RPT. So please have a look on the long video in the offline session.
Hello everyone, this is Yiwei Chen from Samsung Research, China, Beijing. I'm presenting our work, Adaptive Focused Discriminative Segmentation Tracker, which involves the accuracy and robustness improvement on the existing D3S tracker from three aspects. A powerful online target appearance model with initialization from offline pre-trained parameters. A fine segmentation model with the assistance from LU optimization and boundary prediction. An adaptive prediction strategy to update the target appearance model from bounding box and mask information. Compared with SOTA trackers, our tracker achieves satisfying performance improvement on VOT 2020. Meanwhile, the visualization results also shows better segmentation quality. Thank you.
Our next contribution.
Hello everyone, my name is Ding Ma, I come from Harbin Institute of Technology. Today I will give you a presentation named Cascaded Tracking via Pyramid Dense Capsules. The main contributions are summarized as follows. Firstly, we propose a pyramid dense capsule model to capture the multi-scaled spatial relationships within the target. Secondly, we propose a cascaded PD caps to avoid the mismatch with gradually improve the quality of candidates during training and inference time. Thirdly, evaluations demonstrate the outstanding performance of our tracker on 5 benchmarks. Here is the main framework of our tracker. The whole network consists of a feature extractor and multi-stage models. The architecture of PD caps is shown in this figure. The detailed architecture of 2 heads are in the above. And changes the distribution of hypotheses are shown in bottom. Our tracker achieves comprehensive experiments on 5 benchmark datasets. This page shows the effectiveness of cascaded architecture and capsule model. Here is the qualitative results. Thank you.
Okay, so this was the last presentation. Sorry. But this last presentation. This last presentation was actually the only contribution which was a rejected actually ECCV paper. And was actually then finally accepted for VOT challenge because it is really interesting approach, I guess, using capsule networks for tracking. So I would like now to finish this session and would like really to invite you to go to the offline session, to look into these videos and to see this work. I guess you will be able to get in contact with the authors either over the conference system or even maybe you can now contact those people because they are participating here. I would like to also draw attention to our then final live session, which will take place at 5 p.m. UTC or 6 p.m. UTC +1, where we have the winner presentations and where we will have also a 20-minute panel discussion of the various problems and interesting questions you can raise, and also questions which might be raised within the panel. So we invite you to join us in the late afternoon, wherever you are, or in the morning. We are really looking forward to get your ideas, your comments for next year, VOT challenge and workshop. And with this outlook, actually, I would like to conclude this spotlight video session and now hand over to maybe Mate, or otherwise I would finish now, and we see you then in the next live session in the late afternoon. Thank you very much.